Good day to Dr. Go and my fellow friends. We are Group 2, the best team. My name is Edward, and today we're going to discuss our paper, which is Plan on Graph, Self-Correcting Adaptive Planning of Large Language Models on Knowledge Graph. So this is the table of content. So large language models are powerful, but they often hallucinate or rely on outdated information. While knowledge graph provide the factual grounding they need, most current methods are too rigid. One wrong step and the entire reasoning chain fails. So this Neuro IBS paper will introduce Plan on Graph or POG to solve this through adaptive planning. So POG transforms the LLM into a self-correcting agent. It operates on three mechanisms: guidance, which breaks complex questions into manageable subgoals; memory, which tracks the search history so the model doesn't lose focus; and most importantly, reflection. Unlike previous models that follow a one-way path, POG constantly evaluates its progress. If it hits a dead end or realizes it's on the wrong track, it has the unique ability to backtrack and try a new path. This mimics human-like problem-solving on massive data structure.
Hi, my name is Hujay, and I'll be covering the background and motivation for this paper. So, this paper starts with a common problem found in LLMs, where although they are used in many different tasks, such as question answering and text generation, they tend to hallucinate and generate wrong or outdated answers due to a lack of factual information. So, knowledge graphs are a natural fix to this because they store real world factual knowledge as structured triples. This makes their information traceable and editable. And unlike an LLM, where their parameters are frozen, a knowledge graph can be updated as information changes. So, there are existing works that combine the two to create KG augmented LLM methods, where the LLM acts as a reasoning agent that navigates the knowledge graph. And the motivation for this paper is to solve the weakness of these existing methods, because previous methods often follow a fixed path and cannot easily recover when the path is wrong. And Plan on Graph tries to make the LLM behave more like an agent that can plan, remember, reflect, and correct itself. With that, I'll pass the mic to MH to cover the research gaps. Thank you.
Thank you, Jay. My name is Hua Ming Hong, and I will talk about the research gap. So, the problem encountered is the fixed breadth. Existing KG augmented LLM methods still depend on manually predefined exploration breadth, meaning someone has to set the search range manually. Next is the irreversible exploration. Because that breadth is fixed, so the model may miss the correct reasoning path, or end up exploring too many irrelevant paths with no way to fix it. Third, forgetting partial conditions. When questions have multiple conditions, LLMs may forget some of them along the way, leading to incomplete answers. Now I'll pass to Sean to continue.
So hi, I'm Sean Wee. So I'll be talking about the proposed solution. This is the proposed solution called a plan on graph or a POG. The process starts with a question where POG first break the question into smaller tasks, then explores the knowledge graph for relevant information. Next, it updates the memory with the retrieved path and entities. After that, POG reflects on whether the reasoning path is correct, and if needed, it performs self-correction before generating the final answer. So as mentioned before by my teammates, POG consists of four main components, which are task decomposition, path exploration, memory updating, and also evaluation with reflection. These components help the LLM reasons more accurately and self-correct during the reasoning process. So, and this slide shows the complete workflow using a Taylor Swift example. POG first decompose the question into smaller objectives, then explore the different path in knowledge graph and also store useful information into memory. During evaluation, if the current path is wrong or insufficient, POG reflects and explores another path. And finally, after self-correction, POG finds the correct answer, which is blank space. And this is all of my part. I'll pass to my next teammate.
Okay, thank you, Sean. Good morning. My name is Grayson, and I'll be presenting the core mechanisms of plan on graph, which falls into three parts. The three core mechanisms are guidance, memory, and reflection. The first mechanism is guidance. POG will break down the task into multiple sub-objectives, which act as guidance for path exploration. To solve each sub-objective, the LM is able to adaptively explore the POG and examine all the necessary entities and graph relations. This eliminates the traditional fixed breadth algorithm's weakness of limited hops that forces premature knowledge search and disruptive truncation. Next mechanism is about the memory of POG. The three recorded information included the search subgraph, which has all retrieved relations and entities which can be utilized during reflection. The reasoning path is also memorized to preserve semantic structure within the KG. A list of subjective status is constantly monitored, which helps the LM remember known information and current exploration direction. It ensures the LLM does not hallucinate during exploration and reflection. Lastly, the mechanism of POG to be discussed is reflection. After exploration and memory updates, POG will prompt the LLM to reflect whether current obtained information with subjective status are sufficient to provide an answer. If not, the POG will continue down the exploration path to obtain more information, or it could determine the current path is wrong. Then each node along is reevaluated until another path trajectory is selected. The LLM will continue the search until the correct knowledge is reached by self-correction. As such, my part ends here, and I'll pass the presentation to Zikian.
I'm Zikim. I will continue with the discussion of experimental setup and result. The dataset that I am using in the paper will be complex web question semantic process, and real question answering. The evaluation matrix used for benchmark is hits at 1 per exact match accuracy. The next will be performance comparison. POG have achieved the best performance across the three datasets which have outperformed the SOTA baseline TOG, no matter GPT 3.5 or GPT-4 are used as the underlying LM. Because of TOG used the fixed breadth, it shows limitation in effect and efficiency. So POG designed a self-correction and adaptive planning mechanism which have improved both performance and efficiency. Next, the application study. Without memory, it have no sufficient information support for POG in navigating the exploration path, which have shown significant drops. Without reflection, POG cannot self-correct wrong reasoning path. Without adaptive breadth, POG will exploring with a fixed breadth but does not drop much because of memory and reflection ensure the POG able to self-correct. Next, the efficient study. POG require fewer LM interaction, highlights more better reasoning ability. It shows a significant advantage in both input and output token, which have decreased roughly 76.2% from TOG. It have achieved a superior time efficiency to TOG, which have present a speed up of 4 times from 3 datasets. The case study that COT result is failed to answer properly. TOG give an incorrect answer because of exploring wrong path. POG show the correct answer because it find the movie take place in Panama and reflects when information is insufficient, and it correct the reasoning path. That's all for me. Thank you.
Hi, my name is Nigel, and I'll be sharing the strengths and weaknesses of POG. First, POG has several strengths. It improves factual reasoning by using the knowledge graph as an external knowledge source. So the LLM does not only rely on its internal memory. It also supports adaptive graph exploration, meaning that it can choose relevant paths more flexibly. Another important strength is self-correction. When a reasoning path is wrong, POG can reflect and correct the path. This makes the answer more reliable, efficient, and transparent because the reasoning path can be traced. However, POG has limitations. It still depends on the quality and completeness of the knowledge graph. If the correct fact is missing from the KG, POG may still fail. Also, the reflection process depends on LLM's judgment. So incorrect inflection can lead to a wrong correction. Besides that, the paper mainly tested on POG on KGQA datasets. So its performance in real-world agentic AI tasks still needs more validations. Lastly, POG is not a pure DRM method, but more related to LLM agentic planning and self-correction. This research is important because it shows how LLM agents can become more trustworthy. Instead of directly generating pure answers, POG allows the LLM to use external knowledge, plan multi-step reasoning, maintain memory, reflects on mistakes, and self-correct during reasoning. This is meaningful for agentic AI because future AI systems should not only answer questions, but also check evidence and correct themselves when needed. That's all from me, and I'll pass it to Meng Hong.
Thank you, Nigel. So, what does plan on graph contribute to agentic AI? Why does plan on graph make LLM more agent-like? Because the models does not answer directly. Instead, it goes through a loop. It first makes a plan, then it researches the knowledge graph for information. It looks at what it found and saves the user parts to memory. After that, it thinks about whether its answer makes sense. If not, it fixes itself and goes through the loop again. So instead of giving one quick answer and moving on, the AI keeps checking and improving until it's confident. That's what makes it more agent-like. because it actually thinks through the problem step by step.
In conclusion, POG is 4 times faster than previous methods and even outperforms GPT-4 in accuracy. Ultimately, this research proves that for AI to be truly reliable in knowledge-heavy tasks, it needs to reflect on its own mistake. POG is a significant step towards making AI reasoning more transparent, efficient, and autonomous. Thank you everyone for listening to our presentation.